Okay, so after step 1, 2, 3, now we actually can reduce our problem to this. The objective function is still the same, but first, you only have one IR constraint. And also, you now do not need that huge set of global IC constraints. All you need is local IC, okay, local IC, which is the first order condition for global IC, and monotonicity. Our step 4 would be to ignore the monotonicity constraints for a while. So we're going to remove this for a while and focus on the other two sets of constraints. We will find the optimal solution of the relaxed program, okay? And then we will go back to verify that our optimal solution of the relaxed program really satisfies the monotonicity constraints. Okay, if that's the case, then we're done. So now in our reduced program, we only have two sets of constraints, one IR and a few local IC. Now let's look at this. I have defined this function w of theta hat, right? This is the type theta consumer's utility of reporting data hat. Now if we maximize it, we're going to get theta as the optimal solution because we have IC constraints. So by definition, I'm going to say if I plug in the optimal solution, then that should be W of theta theta, which is just W theta. So I define W theta as type theta consumer's equilibrium utility. Okay, eventually he will tell the truth. So W of theta, one parameter theta is enough to denote his equilibrium utility. Now, according to my envelope theorem, I can show how W of theta is affected by theta. Okay, so by definition, I have this W theta is a function of theta, so we can find its derivative with respect to theta. And the envelope theorem tells us that I can first treat theta hat as a constant. Okay, theta hat is my variable. I treat my variable as constant and take the derivative with respect to my parameter. After that, I'm going to plug in back my optimal solution, which is just theta, about telling the truth. So I now want to take derivative with respect to theta, and this is my W theta hat. If I treat theta hat as a constant, then the derivative would just be V of Q of theta hat, because the only variable is here. Okay, when I take derivative with respect to theta. So now I have this, and the last step is to plug in theta hat according to our optimal solution. That's this. Okay, so I can show that W prime of theta is V of Q of theta. V of Q of theta. Okay, this must be true as long as I have my IRIC constraints. Okay. One thing that I want to remind you is that actually you can prove this without using the envelope theorem as a general tool. You can still prove it by using your local IC constraints. Okay, you can first say that you want to do a differentiation for W of theta W of theta, okay, which is this guy. Okay, if you plug in theta before you do the differentiation, then you get this, and then you will differentiate this one with respect to theta. Then this, and this, they are all variables. So you are going to use the chain rule once and twice to get a quite complicated thing. But then because you have local IC, a lot of terms would cancel each other, and eventually you will get the same thing. Okay, so maybe you want to try it at home. Okay, so now we have this. Let's see how that can help us. Now you have this particular thing, right? What does that imply? That implies given any theta, I now can write down its equilibrium utility like this. Okay? Eventually, I have a base which is W of theta 0. And then from theta 0, I go up to theta. And throughout the path, I collect all the increments I should get. Okay, all the increments I should get. Here, this guy is W prime of theta. So again, you are applying the basic, the fundamental theorem of calculus. Okay, so you start from here, go up to theta, and collect all the increments, all the infinitesimal increments, and that goes to your W theta. And don't forget, W of theta 0 is this one. This is the type theta 0 consumer's equilibrium utility, the lowest type consumer's equilibrium utility. We know a few things. First, V is a non-negative quantity. Okay, for any Q, V of Q is non-negative. This means that all the guys whose type is greater than theta 0 would earn more than the lowest type. Okay, would earn more than the lowest type. So that's something that you can understand. And then, given that, there is really no reason for you to give that particular guy, to give the lowest type any utility. Okay, it's safe for you to set its utility to be 0, which means to make the IR constraint, to make the remaining IR constraint binding. Okay, even if you do that, all other types they will be willing to choose their contracts because they can still earn a positive amount. Okay, so now we can say the IR constraint must be satisfied if we set it as a binding constraint. And once we do that, this term would become 0. Okay, and that means all you have is this part, which is this part. And now recall that you have defined W of theta as what? As Q of V, theta times V of Q of theta minus T of theta. Okay, W has been defined to be the utility. Okay, theta V of Q of theta minus T of theta. So what you get here is just by definition. Okay, you flip the signs of from here to that to here, and then you replace W of theta by what you just derived. Okay, so at any optimal solution, your T should be a function of Q in this way. T should be a function of Q in this way. So now let's plug in T into our objective function and continue. Our program can be further reduced in this way. T is here, okay, and I replace T by what we just derived. For every theta, T of theta should be exactly this, okay, according to our derivation. So now our problem would just be this one. Now we don't really need those IRIC constraints. Let's focus on this unconstrained problem to see how may we find Q of theta to optimize this guy. Obviously, this is something we need to handle. Okay, and now it's time to use integration by parts. So let's focus on this double integral. Okay, if you go back to look at the objective function, this is that double integral within your objective function. with integration by parts, we're going to solve it. So that this part to be our u, and f of theta d theta be our dv, and then u goes to here. For dv, we need to find its v, and for small f, its integral is just capital F. So we get this. And then here, we have theta 0 and theta 1 as our lower bound and upper bound, so it's here, and they are here again. And we finally have v du. V is here, right? And the du, you know how to do it, because if you differentiate this guy with respect to theta, then you're just going to get something inside. Theorem of calculus, fundamental theorem of calculus. Now you plug in theta 0 into here, theta 1 into here. The interesting thing is that if you plug in theta 0 here, f of theta 0 would just be 0, because theta 0 is the smallest possible value. Okay, so that term would just disappear. If you plug in theta 1 here, f of theta 1 would be 1. So all you have is here. Okay, is this term, with theta becomes theta 1. For the second term, let's still put it here. So now the two terms can actually be combined, because you are doing the integration from the same point to the same point with respect to the same variable. So all we are doing now is to combine the two terms so that you get 1 minus capital F times v of q as your integrand. So with integration by parts, this double integral can be removed, and all you have would be something like this. Okay, 1 minus f, v of q. Here you have an f of theta, because here you want to multiply the integrand by f of theta. If you want to do that, you need to also divide it, so that here you have f of theta, so that you can really replace the double integral by this term. Okay, by this term. And now you see why you need to have some idea about the hazard rate, because it shows up here during your derivation. Okay, lastly, we want to find q to solve this particular program. So still here you have so many variables, but the interesting part, or the easy part, is that all these problems are independent. You can solve q of theta for each theta independently. And why is that? Because they are not connected with each other. Okay, so we call this point-wise optimization, because you have a lot of points locating on one interval. You want to solve for all the points one by one. For this point, solve it. For that point, solve it. Point and points, they are not related to each other. So we want to do this point-wise optimization. For each theta, I want to focus on just the integral. I don't really care about small f, because it has nothing to do with my q. Okay, and I also don't need to care about the integral. So I only focus on the integrand. And now q of theta is my decision variable. So I want to find q star of theta according to the first order condition. This part is just a constant. V becomes v prime. Q becomes 1. So this is my first order condition. Okay, my q star should satisfy this equality. Of course, if for some theta the equation cannot be satisfied, for example when this part is negative, then your q star should just be 0. And you also have this when you have only two types, right? There is a possibility that you don't want to serve the low type. Here is the same thing. If your theta is, for example, too small, then you may want to ignore those consumers. That's possible. Your T star can also be found according to the formula that you derived a few slides ago. Okay, so the last step is to check that we really satisfy monotonicity and the local IC because we somewhat removed them or ignored them during the derivation. So is that true? Your Q star satisfies this. For each theta, you have one Q star of theta, and that should satisfy this. So if that's the case, then let's focus on this equality. By assumption, this ratio is decreasing in theta. Okay, we assumed that for theta, the hazard rate is increasing. So this ratio would decrease. And then theta minus the reciprocal of hazard rate would increase. So this part is increasing. The right hand side is constant. So when your theta goes up, this goes up. That means V prime must go down. So V prime of Q star must go down. And because V prime is a decreasing function, so if you need this function to decrease, that means your Q must increase. Okay, so that's how you show your monotonicity. Your monotonicity really comes from your assumption that this guy is decreasing. And then you can also verify your local IC. We know that our optimal contract must satisfy this equality. The payment, the transfer, must be a function of quantity in this way. If you differentiate both sides with respect to theta, okay, t becomes t prime. Here you need to apply the chain rule, and here if you take the derivative, you will get just v of q theta because of the theorem of calculus. And then this cancels that. You really get this and that, okay, which is exactly your local IC. That means for any Q, if you always set your T in this way, then local IC is fine. Okay, so you can see that even though we have removed the monotonicity constraints, we can still satisfy it with our optimal solution. Then our optimal solution is really optimal, and your Q should be defined in this way, your T should be defined in this way, then you have the optimal solution. Okay.